Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to tonight's Contemporary Science Issues and Innovations program. The topic is nanotechnology, the field of the tiniest devices where spectacular innovations are the norm. Our guest, Dr. Samir Sonkusale, is the director of the famous Nano Lab at Tufts University. He is also professor of electrical and computer engineering and also professor of biomedical engineering at Tufts. Dr. Sonkusale is a leader in the development of nanotech medical innovations especially. Tonight he explains how and why nanotech is revolutionizing medicine and other fields, and he describes some of the unique sensing devices created in the Nano Lab. We are most honored to welcome Dr. Samir Sonkusale. Welcome, sir. I'd like to start by asking you something general about this field, and that is what is nanotech? What is that space that is the basis of all this wonderful innovation?
Yeah, thanks for that question. So nanotechnology, by the very word, is we are talking about dimensions in nanometers, which is almost as small as a marble would be to an earth.
Okay.
So that's the relevant size scale. So a marble would be a nanometer to what the size of the earth would be.
Okay.
So it's really, really small. And these, all the matter in the universe is made of building blocks that start with atoms and molecules. And if you build it up into space, so we are looking at dimensions from 1 nanometers to 100 nanometers. And at this scale, you can harness the property of materials that are unique at that scale. So a bulk material, which is a large scale material, would behave differently. And then when you keep making it down, just shrinking the size from, let's say, a millimeter scale device to a micron scale device, which is 1,000th of a millimeter, would not give you that advantage. You have to go even smaller and smaller, and suddenly some interesting quantum physical effects start to manifest itself. And if you can somehow harness that by using them in some special way, then you can get very interesting properties. And so now basically what you have is another dimension of same material giving you another dimension of properties that you didn't know you had before. And so now if you can build your own matter or devices nanometer scale at a time and build them up into a building block that you decide the rules of how you putting them together, now you created a matter that can do very interesting things.
So that's what one of the things you can do. I understand with this very small scale, you can penetrate, say, organs and blood vessels and stuff where you wouldn't be able to do that so easily before. But it sounds as though you have some other unique features at that level. Is that the case? That is the advantage?
Exactly. So, for example, I mean, I could say a copper is not transparent to light, right? So you see, but if you make it thin and small enough to nanometer scale, it's transparent. Or if you look at any other material like silicon, which is the one that's used in all our circuits, it's not flexible, it is brittle. But if you go down thin enough, really thin at the nanometer scale, it's become flexible and pliable as if it's a piece of plastic.
So it just changes altogether.
It just changes properties. It gives you these very interesting behavior. Things we consider gold as a very stable, inert material that doesn't react with anything. Well, guess what? If you go to nanometer scale, it's the most catalytically active material. It can catalyze chemical reactions so fast that if you were a large bulk material, it would not be catalyzing. It would be inert. So it is just amazing surface properties. When you get smaller, you have more surface and less volume. So you have more, I would say, reaction sites for catalyzing reactions. Or just confining something small, you basically create discrete quantum levels in some energy levels that you can begin to harness for a variety of physical or chemical things.
That is fascinating. Would you say that they're just at the beginning of the discoveries, or have they, in the field generally, made a huge amount of progress and they know all about these things?
Yeah, I mean, in some ways, we've been working with nanomaterials without knowing it for a long time. So the stained glasses in those old churches are essentially, they are not dyes, they are not pigments. They are actually nanoscale metals that are embedded in the glass, and that's what gives them color, which does not fade away. Right?
And that's why they don't fade.
That's why they don't fade away. It's because it's a structural color. It's not coming from chemical dyes or pigments. It's coming from the fact that there are nanometer scale devices of certain size. So in some ways, we've been working with nanoscale materials for a very long time. But the resurgence in being able to control the size and the properties of nanoscale, I would say, is probably 2 or 3 decades, which is fairly recent in considering scientific innovations. But we are now beginning to come to a place where we are beginning to use this in our day-to-day applications. Some of the new devices or consumer electronics or sensors are beginning to harness the power of these nanoscale materials and nanoscale devices.
Right. And your lab is a great example of this. The diversity of these, not instruments, devices, whatever that you have come up with. That's amazing, and that's one piece of an entire field. But it sounds as though this could really be tremendously revolutionizing in many areas.
Precisely. I think there is a lot of, in my group, we are working on some very key, interesting applications. But if you look at the overall field, there is a lot of development in electronics. Right? So your phones are working faster, you're accessing internet faster, everything is just connected. It is basically because of nanoscale transistors. These electronic circuits that operate with devices that are that small. And we are also looking at a lot of medical devices, treatments, new treatments coming up. I don't work on those, but some of those new treatments uses nanomedicine. Some of these nanoscale particles that can deliver drugs to tumors and kill tumors on demand. And so there is this huge interest in doing nanomedicine, nanoelectronics. There's a lot of application in energy and environment, which is using catalysis to make earth-friendly fuels and batteries and solar cells and all kinds of, and that would revolutionize energy and environment because they are linked in some ways. And so there's a lot of different opportunities where this will, the nanotechnology has a role to play.
It is really neat, isn't it? Tell us about your lab. I know you have developed a number of things. We've done a program on in your lab, but for instance, and you've talked about them elsewhere, but it seems as though you're constantly coming out with something really new. What some favorite items?
Yes, definitely. I'm very happy to talk about some of the research activities in my lab. So we use nano materials and nanoscale engineering as a way to make more practical, useful devices. We are working at the frontiers of, I would say, making what I could call low-cost diagnostics. For example, over the years, we worked on some chemical sensors, which uses nanoscale materials like carbon nanotubes. These are tiny rolled up carbons that you can, they have a large surface area, and so you can functionalize them with sensing chemistry that would then sense your target of interest. So we've been using some of these nanomaterials like carbon nanotubes. We've also used flat carbon, which is almost an atomically thin carbon. It's a plane.
Like 2D or
it's
something.
a two-dimensional
Yeah,
carbon.
yeah.
We call them, they are graphene, which is
Yeah.
opened up carbon. And there is a reduced form of graphene, which is just another impure form of that graphene. But it has an interesting property that it has a lot of surface area. So it's essentially, you can chemically functionalize them with things that would then sense the target that you're interested in. So we made a lot of these chemical sensors, and interestingly, even though it sounds as if we are working with such small scale devices, we would need expensive instruments to do that. We essentially do not. We do this, what I call just a wet chemistry. It's a bench you develop these nanomaterials on a bench top in a not so expensive environment, and then figure out very simple ways of patterning them on substrate. So we take these nanomaterials, we bring them on substrate meaning any surface, and then we basically make them, we treat them, and then we essentially use them on the field right away. So for example, in one applications, we used some of these different nanomaterials for sensing volatile vapors from human breath. So our human breath carries a lot of very useful markers of our own
So
health.
that's something.
And so now these nanomaterials are very sensitive to even a small change in your human breath levels, and that can be used to detect whether you have a certain medical condition. And so, for example, we have made an array of these sensors using different nanomaterials to detect specific volatile markers for detection of an infection in your stomach called H. pylori, which is sort of a precursor to a lot of stomach cancers in the developing world. So you can basically, from changes in the breath pattern, you can basically monitor sort of this infection in your stomach. This is just one example, and these sensors are not. They're fairly straightforward to make, and you're welcome to anyone who's listening to this. Welcome to visit our website and sort of find out more about this, and I'm happy to talk to them in person as well. But it is, I would say, it's a process that anyone, anywhere can sort of incorporate fairly easily to sort of make these platforms. And all it's doing is harnessing the property of these nanomaterials for their extra sensitivity.
That is that hypersensitivity. May I just pursue that for a second? A lot of these tests are very expensive, for one thing, very complicated. Here you have a very simple one, but because of that level, or because of the peculiar capacity of sensing for this device, would that possibly pick up the indicator of a disease that a more elaborate, our usual, what should I say, our standard level technology might not?
Precisely. I mean, I think this nanomaterials offers a very high surface area to a volume ratio, which is kind of just like, as I was mentioning, when things get smaller, they become more catalytically active. And that's just because of this large surface area interaction. Similarly, you are right, and the fact that you now have a lot more sensitivity from these materials allows you to pick up very small changes, parts per billion, parts per trillion, different. And so you have a lot more sensitivity to things that you would otherwise not recognize. So even though they're low cost and easy to make, and they do offer, in some cases, better responsivity than some of the conventional methods that we had access to in the past.
That's most interesting, because it seems as though, for instance, there are several cancers that are not apparent through regular testing until the cancer is really established. It sounds as though you might be able to devise a way to pick up something well before it can be picked up with standard technologies.
Exactly.
That is great.
Yeah, exactly. As the world of medicine is evolving, people are learning different markers in your own blood or in your saliva or in your breath that is indicative of these. And once you are able to figure that out, it will be on the basis of nano-enabled devices that you can then detect for early screening. So the more you find out about your health, what markers are relevant early in the screening process, you will basically be able to detect before it happens.
That is amazing.
Definitely.
And now I'm familiar with you've done things like special sutures,
Yes.
and another was, I think, delivery systems for like a medication, if I recall, and all of this at this tiny scale. And do you still develop these kinds of
Yes,
things?
so that is the other area of research, and we coined this whole notion of what we call smart threads. And so these are basically what I would say your regular textile threads that you would routinely use, or these are medical grade sutures that we essentially build all our devices on them. So imagine in case of a surgical operation, the surgeon stitches up the wound, and then you go home and the wound gets infected. And this is a very common problem, and it's a big liability. If you could embed sensors in that suture that tell the doctor that the surgical process is resulting in an infection, or not even an infection, causes an inflammation or some other adverse reaction, it would be nice to know. But how would you then get these sensors and all this interesting functionality into those threads? So we came up with a process in our lab that essentially takes conventional medical grade sutures and functionalize them by coating some very simple chemistry on the surfaces to embed some of these nanoscale sensing materials on the threads themselves. So in some case, for example, a color would change in these threads. So then you would know the infection's happening. In some other application, we have a little tiny electronics, sort of a size of a button or a small patch that would sit connected to these threads that would give an indicator to a phone saying that there is a reactivity happening on these threads that's indicative of an infection.
Right.
So this is all possible because you're able to sort of engineer. Now this is the engineering part where you take these materials and engineer them onto these threads. So we've done a lot of these smart threads for not just surgical or smart sutures, but also in bandages. So we would make smart bandages where we would have different threads that would sense different things in your wound. And so when you wrap them up, your wound is getting infected, it will tell the doctor again. But at the same time, you just brought up that we can also add drugs to these threads. That instead of sensing, you are now using them as a way to deliver treatment. So imagine the same wound where, let's say, you have to deliver some kind of an antibiotic because you have infection developing. It's already built in, and you only release when
it gets the
the
signal.
sensors get the signal that the infection's there. I should actually be delivering a drug. So these drugs are nanoscale or microscale drug delivery vehicles on the threads, and it's all connected through your phone, or it doesn't have to be. It could be passive, but it could be connected through your phone to your caregiver or your doctor, who can then say, okay, looks like I need to increase the dose. And the person doesn't have to go back to the doctor. The drugs are already in the bandage. They can just say increase dose by remotely. And
let's increase the dose.
that's a little scary that Alexa is controlling your drug. I would, there's an issue of privacy there. I'll stay away from. But the promise is there for letting a little bit more control of precision medicine.
Right. And very direct, very direct.
Very direct. And you're not even abusing the antibiotic.
Right.
You're not delivering excess drugs.
Right.
you're personalizing it to every person. If
And
you
the physicians in all cases are up to date. Yeah.
they are also up to date, and and they can get involved in the treatment even when you are not there in person, which is very useful for rural communities
right,
where you
right.
have to drive really far away. So this whole notion of precision medicine is sort of enabled by these devices that are building upon all these knowledge that we have now gained in nanoscience and nanotechnology, electronics, and so on. And we're basically trying to put them together into these very useful practical devices.
This is really exciting. You mentioned also that you're doing work on like environment related nanotech as well. Can you tell me something about that?
So yeah, that was a very good question. So when I talk about environment, I'm looking at ways we understand how we impact the environment and how environment impacts us. So in my group, when we are looking at environment, we would like to make sure that we understand the environmental pollution around us.
Yes.
So we made some of these very thread-based sensors that would change color, for example, when you enter a room, if there is a certain high level of pollution in the
particular pollution
in the environment. So these are what we call colorimetric smart threads. These are very very direct visual sort of readout of color change in the basis of pollution. You can also use them to monitor water quality in your house. So if you imagine you have these sensors that are easy, low cost, disposable,
right.
You are essentially enabling the population, the general masses, to have these sensors. Then you are collectively monitoring.
Yes, I was going to say.
You're not relying on an EPA or an agency to tell
right.
you that your environment is polluted.
I was thinking of the PFOS problem, like in the city, yes,
Yeah,
that where there was so much denial. And
yeah, and you don't need to. It is one of those places where I think you have a way to make low-cost platforms or sensors that you can that can be handed to general population, and they are more involved in their own
right, and empowered
in their own so they can see my water has more lead, or my water has more pollution, or they are more informed because they are driving to work every day and they take this road which has a huge amount of pollution, that their fabrics are changing color because of our sensors.
Very good.
They would try to make some adjustments in their day-to-day life. So you, in some ways, you're learning more about the environment, but then you're also being empowered, means you're also impacting the environment.
Right, but that changes how you function as a citizen, doesn't it? I
Exactly.
mean, because you're constantly learning in this manner, but it's that sense that you can do something about it. You don't have to wait for this test and that test, it will show up.
Precisely.
That is really incredible.
Exactly. I think that's basically the power of having citizen science. Everybody basically has the ability to use these sensors, these platforms, and make decisions about their health, their environment.
Right, to become much more participating citizens. You have, speaking sort of on that you have worked hard to make this sort of development available to developing nations or whatever. I don't know if it's very expensive to set up these kinds of labs. You have to have very specialized people, obviously, and so on. But you've done a lot of work to make this much more available around the world. Can you tell us something about that?
Yes, I'd be very happy to. Yeah, so one of the principles we've always followed in the research in my group is to the rule of simplicity and frugal engineering. If you're making platforms and devices, being mindful of the resources and the equipment and the infrastructure that you need to make them, and if you ensure that whatever you're doing to make the devices or platforms is something that can be easily ported to a developing world, it is then you are on the right track in terms of that particular project or in terms of engineering that device. So most of the techniques, for example, the smart threads, they rely on conventional threads and your ability to dip and coat them, which is sort of a very old, 1,000-year-old fabric textile. Everyone's making clothes and inking a thread.
Right.
Inking a thread is just, just change the ink. The ink is now smart and functional. So basically taken that approach. So
Yes.
the approaches we use are screen printing, which is sort of printing newspapers,
Right,
or literally what I would call using all the tools and techniques that are already accessible to anyone. So the idea is to basically, when we say we use the word do-it-yourself diagnostics in the context of medical, is something that we don't just dispense the devices to the developing world, but instead we dispense the technique to make your own devices.
Right.
And so when I go and travel around the world, and give talks, even this last week we actually had a workshop in India where we actually had students make their own sensors and test their own breath.
And they can do it.
And they can do that right there with very simple processing steps involved. So there will be very little. There is of course a little bit of learning curve and a little bit of materials and supplies, but it's still, most of it is something that can be easily translated.
What you are distributing is, in terms of the learning process, is stuff that most of us can do. We don't have to run out and get a PhD in engineering to do this, but you could really do a lot with that, and it would be very encouraging to people. You have an emphasis also, I think, from having a kind of an international perspective. That's a default setting. You have students from all over the world in your lab, and I wonder, is that deliberate or is that a commitment?
It's a very good question. I would say it's a mixture of both. Being in the U.S. Gives us the flex. It's an amazing place where everyone from around the world, the bright minds, want to come here and participate in this innovation process. And I think that's the fortune we have as a researcher of being in the U.S. and doing research here. At the same time, and there is a commitment as well. In the commitment is that the science is for the world, for the sharing, and whatever developments we make here doesn't just affect us, it affects the entire humanity, the entire planet, the entire Earth. So in some ways we have to make sure that, at least in my group, is have a way that whatever we do, both in terms of the personal we have in our group, the science we do, and the interactions we have around the world is sort of global and has the global perspective.
Yes, I see it in a lot of sciences anyway, but that it's very international.
Very international.
And that is the new thing. They have superseded this national kind of mentality or something, and they've moved on in this direction, which is really exciting. But can you give me an idea of the nationalities in your lab at present? I'm sure it changes over time.
Yes,
just about everything.
So exactly. it's a flow and different.
Yes,
we have Chinese, we have Indian, we have Korean. I have Iranian students. I also have some Egyptian, and there are some Bangladeshis, and I can also go beyond my lab, surrounding labs in my group. We have people from Europe and Africa, and so there's a lot of.
I would just think it'd be very exciting to be in that environment.
Precisely.
Absolutely, a wonderful thing to be in that environment. And it reminds me, at CERN, at the Large Hadron Collider, they say that, of course, they have thousands of people there, and that some of these people that sit side by side would be at war with each other if they were out, in the normal life. But that goes completely because of this commitment to the science
and shared mission.
And you have that.
Yeah, precisely. I think those national boundaries would disappear when you're working together on a shared science
Yeah.
mission.
Right. I'd like to know something about your background, particularly here. You have all these degrees and all these, you're a professor in 2 fields at least there. And so is there a way to get into this field? Is that, would you have to have the electrical engineering or the whatever the engineering, specific engineering to get into this field, or could you come in through a side door?
Yeah, I always said this. I think nanoscale and nanoscience is at a stage where even if you're a high schooler, you should be able to.
Isn't that interesting?
You don't need to have a degree to sort of start working with or interacting or learning about this field. And nanoscience and nanoengineering, this whole, or nanotechnology in general, is a field where there are people in chemistry working on this,
Yeah.
there are people in electrical engineering working on this, there are people in mechanical engineering working on this. So it's a truly interdisciplinary field that you can come in, whoever you are, from whichever angle. If you're interested in science in any way, either you're interested in the final application, that you want to do some new drug design or new devices, or you're interested in understanding the fundamentals, you can come in at any point in time and learn. So it is not a field that is restrictive in some ways. And there's this whole notion of project-based learning around
Yes,
curriculum,
yeah.
where the idea of learning, you could start by doing.
Yes.
And nanoscience and nanoengineering is a place where you can actually really learn by doing. And there's a lot more to learn. And even today I'm learning as we are working on different things. And so I would encourage anyone who is interested in this field to basically just say, I want to get started. This sounds very exciting. Start by picking a problem that you want to solve, and just sort of approach a scientist, a researcher, or a teacher, or anyone who's been working in this field, and you will see how easy it is to sort of get involved and sort of make a contribution, make a difference.
It's really neat.
Yeah.
Did you start out with this field?
No. Actually, my own background. I did my undergraduates in India. I came to the U.S. For my graduate degree. I did my graduate degree in electrical engineering. I designed electronics and circuit boards for many of the phones and the consumer application. I decided I wanted to make some actual practical devices that would away from the more commercial angle, and so I started learning on. So it was sort of over time, when my professional career got into this field of making sensors and devices for medical applications, that I sort of got into this whole field. So as I said, even my journey is a back door.
Yes, yes.
It's not a direct entry into the nanoscience and nanoengineering.
Right. That level by itself is so exciting that I imagine if you encounter that, especially maybe through engineering, you might really get captivated. One off and start doing this. You mentioned that you do all this tabletop stuff, that it doesn't require the elaborate stuff that we often think of with the lab. And I've seen some of the things that you do in your lab, but how can you go about designing and then actually creating the thing, like the bandages or the delivery systems for medications or those sensors?
Yeah, so these tabletop devices, so basically, for example, when we make these smart bandages which have sensors and delivery systems, we have a choice. The choice is you can use the clean room in an expensive facility to make these devices, which would take you on a different path. But there is also a less conventional path where we figure out or we innovate on ways to be able to do that outside the clean room.
Okay.
And so some of the things, in case of bandage, we want to coat the threads with inks that can sense. So the question now is, how do we make the ink? So you decide the problem, that your problem is not to use the existing expensive equipment to make the devices, but sort of identify that core requirement that you can do outside the clean room. So in this
Okay.
case, making an ink that is sensing, if you're delivering drug, making a drug delivery ink.
Right.
So now it's an ink synthesis problem. So can you make the ink that would then basically, so it's a sort of a hybrid of chemistry,
Yes.
a little bit of chemistry, but once we figure out the recipe, it's universally applicable.
Okay.
So it's one of those things where we make the effort to develop these processes and methods that are simple enough for anyone else to replicate.
Yeah.
And so in our case, when we are making these sensing threads, we have to make these sensing inks and how to coat the threads, the
Okay.
processes, which are all tabletop. So it requires at the maximum some maybe a heater, a little bit of a heating unit,
A computer, maybe
a computer here
some
and
thread.
there, some threads, some chemicals that you can, and every once in a while you might need some slightly more expensive, hopefully in less quantity, to basically make the things functional.
Okay, then after you get the design, so to speak, and the solutions all figured out, how do you get them tiny enough to, I say, if these are things that you inject, you just squirt them into the system or something and tell them where to head?
No. So this is where my research is sort of different. We harness the property of nanomaterials, but the devices are still microscale. So the individual elements on the thread are nanoscale devices, but they're still arranged. There are a lot of them on a thread, so they're still microscale devices, which is much larger than the nanoscale format. And so we sort of use the nanoscale properties at the large scale. We don't, beyond my group, other researchers who've been developing these drugs using nanomedicine, where they use nanoparticles, they functionalize nanoparticles, they still synthesize a lot of nanoparticles
I see.
in bulk. As long as they have control over what each individual nanoparticle binds to,
Okay.
they still synthesize a lot of them.
Okay.
And then what they do is they basically, let's say you are targeting tumor, they would inject them in the blood and they would use a magnetic.
Yes.
So they can probably have a magnet, or they can use chemical targeting.
Right.
Where there are some sensing elements on these nanoparticles that would seek out tumor, because
Okay.
tumors express those more than others. And so they go themselves to those tumors, and then once they bind them, then you come from the outside and shine light or magnetic field, and they just heat up the tumor and kill them.
That is fascinating,
So
right?
yeah, but they're still working with lots of particles.
Right. But there's not some conversion to the nano level necessarily. You just work this stuff out and it operates
Yes,
at the
exactly.
nano level. And then discovering the properties of, say, gold at nano level and
Exactly.
stuff, that's another kind of investigation.
Yes, I think
These
that
properties of
precisely. There's a lot of
minerals and-
very interesting material scientists and physicists and chemists who are unraveling new insights into these nanomaterials. As engineers, I'm very happy to see a lot of choices for me to play with
Oh,
and
I
bring
bet.
to the devices. So there are a lot of these very exciting work that the chemists and physicists and material scientists are doing, figuring out new materials. And I
Yeah.
hear new materials every day that are coming up. They're coming up with very interesting properties. Some have synthesized them, some have numerically found out or theoretically found out
Yeah.
interesting properties, but have not yet synthesized.
yeah.
So there's a lot of opportunities there for anyone to get into. And
What
yeah.
a field.
Yeah,
What a
exactly.
field. And it can do so many things. You concentrated on a couple of areas, but where do you see this going in, say, 20 years if we survive here? that this field will have, considering what you have suggested in terms of environmental stuff, energy stuff, obviously technology stuff, medical stuff, the capabilities of this field, will it just supplant some of the things that exist now that are large scale?
They will be part of those still. So I
Okay.
think they will just permeate. They will permeate sort of everything we do and interact. Your textiles that is sensing your vital signs.
Yes, isn't that something?
And your, the everything around you basically sensing the environment and your health in some ways is being enabled by advances in nanotechnology. Hopefully, our understanding and travel to in space would be enabled by advances in nanotechnology. There are new
Hadn't thought of
frontiers
that,
and so there are lots of very interesting possibilities for nanoscience. I think it'll not supplant, it'll just become part of our day-to-day existence. It'll just make things smarter and better, hopefully.
It's so neat. That to end, since we're running out of time, I'd just like to know what your current project, your favorite area or project is.
I enjoy working in the field of medicine and biomedical diagnostics. So we are still continuing to make a new generation of sensors and diagnostic platforms that can detect biomarkers in saliva, in breath, and so on. We are also making a next generation of platforms in the form of a pill or a capsule that would have some of these sensors that we can basically swallow and do some diagnosis and sort of understand our gut microbiome. So there is a lot of interest in that. And this doesn't require just nanotechnology, other fields as well.
Right.
There are a lot of very interesting possibilities we are looking at, mostly in the field of medical diagnostics.
Right, right.
Yeah.
What an exciting thing.
Thank you.
The fact that you are eager to share this with the world is a very wonderful thing too.
Thank you.
So thank you, because that's, I hope that a lot of young people will be encouraged to start looking at this field because the prospects seem to be endless. So
I hope so.
But thank you so much for all this wonderful information and all the best for that Nano Lab.
Thank you. Thank you so much. I'm glad to be here.